Assalamu alaikum wa rahmatullahi wa barakatuh. We discussed about the basic parameters of the op-amp, and you got some overview about the uh, operational amplifier. Now uh, we will discuss something more about the common mode rejection ratio. So we have discussed many things about common mode rejection ratio. So the common mode rejection ratio is usually expressed in dB, okay, and it is 20 log the open loop gain or the differential gain. So it is also known as differential gain divided by the common mode gain. For example, we have suppose how can I find the open loop gain if everything is given? Suppose for example, if I am giving you the common mode gain as 1 and the common mode rejection ratio in dB as 120 decibel, okay, how to find the open loop gain or the differential gain? Okay, this is the differential gain. So how to find the differential gain? So you know that the common mode rejection ratio, we have this equation, common mode rejection ratio in dB is equal to 20 log AOL by ACM. Now I will bring this 20 here. So what I will be getting, common mode rejection ratio in dB divided by 20 will be equal to logarithm. All these logarithm are having the base 10. So please remember this logarithm are having base 10. So AOL by ACM. So I will be taking 10 power on both sides to convert to original value. So 10 power common mode rejection ratio in dB divided by 20 is equal to, if I am taking 10 power in this side, I will be getting just AOL by ACM. So how to find AOL? So I can find AOL as ACM multiplied with 10 power common mode rejection ratio in dB divided by 20. So in our case, it is, you know that the common mode rejection ratio, sorry, the ACM is 1. So 1 into 10 power, the common mode rejection ratio is given as 120. So 120 divided by 20. So you will be getting it as 10 power 6. So you see here the open loop gain is 10 power 6. It is a very, very large number. So usually for the operational amplifier, the common mode rejection ratio will be high, and also the open loop gain, or we can call this as the open loop gain. Another name, it is the differential gain. Okay. So we will be forgetting about the common mode rejection. Sorry, we will be forgetting about the common mode gain usually. Okay. Now we will see. Now let us consider. So you know that for an operational amplifier, for an op-amp, you have seen that the gain, the open loop gain, that means the open loop gain is very high. Okay, it's very high. For example, 10 power 6 is the open loop gain. Now, and the input current, you have seen that the input current, suppose if you take the op-amp, I told you I1 and I2, suppose this is I1 and this is I2. This I1 and I2 both are actually approximately, I1 and I2 approximately everything is same, and it will be approximately 0. It is because the input impedance of the op-amp, I can say it is the input impedance of the op-amp. This is the input impedance for the op-amp is very high. I told you this is tending to infinity, I told you. So the current going inside the op-amp is always 0 in ideal situation. Okay. So for our analysis, we will be using this assumption, and for simplifying our circuit analysis. So assume that you can assume this, you can use this assumption. It's very, very important. Okay. So the Zn is approximately 0. That's it. Okay. And the voltage gain, a open loop gain, is very high. So these assumptions are very important in analyzing the op-amp circuit. So these are very important. Okay, these assumptions are very important. Assumptions are very important in solving circuits or analyzing the circuits. Okay, circuit problems, in solving the circuit problems. Okay, circuits related problems. So this is the situation. Now we will consider an example. You will understand. There is a problem. I told you, you have an op-amp. Okay, this is very important concept. Now in open loop configuration, let us consider an op-amp. Okay, now I am grounding this terminal, so my voltage, it's V2 is equal to 0, and here I am applying some voltage which is let's say it's V1. Okay, and my open loop gain, so forget about the common mode gain, so I can add here one more point. The common mode gain is approximately 0. Okay, so these are all the assumptions I can use. So the common mode gain is approximately 0, so we will not consider the common mode gain at all in the circuit analysis now. Okay, in very precise analysis you can consider, but in the normal circuit analysis, for simplicity, we will not consider the common mode gain. Okay, so it will not come into picture. Now you see here the open loop gain is there. Now what is the difference voltage here? VD. So the difference voltage VD is V1 minus V2. Am I correct? So what is V out? So V out is the open loop gain into VD. Am I correct? Because you are giving the voltage between these two terminals. So V1 is some voltage and V2 is equal to 0. So V out will be equal to AOL into V1 minus V2. So this is what I am going to get as the output. Now let us consider, for example, I am considering an example. Please note this very carefully. For example, let us consider the open loop gain. For example, you have an op-amp with the open loop gain as 10 power 6 or 10 power 5. 10 power 6. Let us consider op-amp as the open loop gain as 10 power 6, like our previous example. And V1 was 1 millivolt and V2 is equal to 0 volt. Now what will be the output? What will be the output? That's very important question. So VD is equal to V1 minus V2, which is equal to 1 millivolt minus 0, right, which is equal to 1 millivolt, and V out is equal to AOL into VD, which is equal to 10 power 6 into 1 millivolt, which is equal to 10 power 6 multiplied with 1 milli is 10 power minus 3. So this much volt, this is equal to 10 power 3 volt. You see here it is 1000 volt. V out is equal to 10 power 3 volt. That means it is 1000 volt. Is it possible? No, it is not possible, because the op-amp cannot produce itself its own voltage, because you know that the voltage is the basically related to the energy. Okay, so it cannot produce the energy by itself. And also you see here for the operational amplifier, if I am considering 741 IC, this is 7 and 4, I will be giving a power supply. This is plus VCC and this is minus VCC or minus VEE. I can consider. Usually this is given as plus 15 volt and this is given as minus 15 volt. Okay, so VEE will be usually minus 15 volt and this is plus 15 volt, but I am getting an output of 1000. Is it possible? No. So what will be the output? So here the output, you see here this is positive sign. The maximum output that we can get is only, so this kind of output is not possible. It's not possible. So even you are giving 1 millivolt, the op-amp is giving you something maximum. So this means that you are getting a maximum. And what is the maximum you can get? You can get a maximum only plus 15. So whenever you are giving 1 millivolt, the op amp will be immediately saturating. You see here, this is a saturation point for the transistors. Saturation. And this is also saturating. Okay. So one of the transistor will be saturating and another will be moving into cutoff. So that's why one of the transistor will be saturating and one will be moving into cutoff. If one is saturating means its output voltage become 0, and if one is moving to cutoff means its voltage become maximum. Okay, plus 15 or minus 15. So you see here the op amps are moving into its maximum. Okay, so in the same situation, in the another situation, suppose if we are giving the V1 not here, if you are giving here also, you will be getting negative. So it will be going into negative minus 15. Okay, so this kind of open loop configuration is a problem basically. So we cannot, so even a voltage V1 is equal to 1 millivolt. Actually, it is giving you something maximum. The transistors are moving into the saturation and cutoff, plus Vmax, which is equal to plus 15. How you can work with large voltages like 1 volt and 2 volt? Even 1 millivolt is giving you the saturation or cutoff. So this is a problem. So to avoid this problem, we use the feedback. That means you will be feeding back your output to the input. Okay, so you will be using the concept of feedback in amplifiers. Okay, so this is very important concept. So we are studying now about the concept of feedback. So how we can avoid this problem? Okay, so here the problem is that it is because the gain of the amplifier, open loop gain, is infinity. So how to control this gain? We want to control the gain of the amplifier. So we want to control the gain of the amplifier. If it is always 10 power 6, or you can say 10 power 6, if it is 10 power 6 is 10 power 6. So but we want to control this gain, okay, without disturbing the internal structure of the amplifier. We cannot do anything, because once you go to the shop and purchase an operational amplifier, you cannot modify it, but you can connect something outside. That means you can use the concept of feedback in the amplifier. So after feeding back, our gain will change. We will call that gain is known as the closed loop gain. So after feeding back, we will be calling our circuit as the closed loop circuit. So previously our circuit was open loop, and now our circuit after feedback, it will become closed loop, and the gain we will call now as new gain, which is nothing but the closed loop gain. So you can have now the gain, you have the gain which is known as the closed loop gain, a closed loop. Okay, we will be representing like this is usually represented as ACL, the closed loop gain. So you can change this closed loop gain from 0 to the open loop gain. Usually the open loop gain, for example, it's 10 power 6. In some amplifier you have more gain also. So you can adjust the gain from 0 to AOL according to your application, according to your requirements. So according to your requirements, okay, according to your requirements. So this is the advantage. So we will talk about now feedback. So we will talk about now feedback. So what do you mean by feedback? That means feedback, sorry. The feedback means actually the part of the output is feeded back into the input side for controlling the gain, basically. Okay, and many other purposes are there that we will see later. So feedback can be classified into two types. We have the first type as the positive feedback, and the second one is the negative feedback. Okay, negative feedback. Okay, but if we use the positive feedback, the problem is if you are taking the output and you will be feeding back positively, that means it will get added with the input. If it get added with the input, your output will become more worse, or it will be going into the transistor will be again moving into saturation or cutoff, so that the output voltage will be maximum plus Vmax or minus Vmax. That is the problem. So positive feedback usually increases the output voltage. Okay, but there are some situations where we need the positive feedback, but it is not generally used in amplifier. But the negative feedback means the output will be fed back negatively. That means that you will be taking the output and it will get subtracted with the input. So because of this subtraction, your output voltage will be reduced and you can control the gain. So we will see all these things so later. So this is good one for amplifiers. So we will be using in amplifiers, we will be using this concept, the negative feedback. So this is what we are going to discuss. But this positive feedback is also useful in certain circuits like oscillators. So we will see that later. It is there for you to study. So oscillators will be using the positive feedback. But now at this point of time, we are talking about the amplifiers. So our amplifiers will be using negative feedback. Okay. Now we will be seeing a circuit. For example, negative feedback circuit. We will be seeing a negative feedback circuit. Sorry. Negative feedback circuit. Okay, we will be seeing a negative feedback circuit. So you have an op amp, you will be giving V in here and you will be getting V out here, but the part of the output will be feeding back, and how much you have to feed back is determined by some circuit here. So we will call this as the negative feedback circuit. Okay, negative feedback circuit or feedback circuit. I will be using FB for feedback, not Facebook. FB is negative feedback circuit. So feedback circuit. Okay, FB is basically meant for feedback. Okay, this I represent using FB, and you see here I am connecting my feedback input. I am connecting my feedback input at the negative terminal. So if I am getting some voltage here, let's say this is Vf, I can represent my overall input as Vd, right? My Vd become, with the feedback, my Vd become, you see here this is connected here to the positive terminal, so plus V in, but my feedback is connected to the negative terminal, so minus Vf. So you see here my input to the op amp, my Vd is now reduced. So you can see here that my Vd is decreased due to feedback. Okay, due to the negative feedback. Okay, negative feedback. But in positive feedback, it will get added basically. But anyway, we will see how we can do all these things. Okay. Because of that, we will be always using the negative feedback to control the gain, so that the total gain, the open loop gain of this op-amp was A or L. But if you see the overall gain, that means the overall gain means what? Now this is in the closed loop. Now this is in the closed loop. So the closed loop gain, we will be calling the closed loop gain as output divided by the input side. So we will be seeing, because you are the observer here and you are the observer, your friend is the observer here. Okay, you will be giving some input here and your friend will be saying, okay, I have got this much outputs. That output by input is nothing but the closed loop gain. So you will not see what is inside the circuit, what is there, closed loop, open loop, all these things. So you can control the gain of the op-amp by using the feedback circuit. So if you have a feedback circuit, according to this feedback circuit, you will be tuning this feedback circuit so that you can control this guy. You can control this gain. You can control this gain. You can control this gain by controlling the feedback circuit. Okay, that is the beauty. So you don't want to touch the op-amp. Okay, you can go to the shop and buy a op-amp with very high gain, but by using some external circuitry, you can control the gain of the op-amp. Okay, so that's what we are going to see. Now we will be seeing a very famous circuit, which is inverting amplifier. This is an amplifier. Okay, that we can control the gain of this amplifier. Now we are using here V in. Now you see here there is a V out. Now we have the feedback circuitry. My feedback circuitry, I will be connecting like this, just with two resistance. This is my feedback. This is RF and this is RI. Okay, this is RF and RI. Now you see I am connecting here. So because of the feedback, I will be getting a voltage here. This is VF, and the voltage at this point, anyway, it's V in. You know, this is V in and this is VF. So I have a voltage here. This is VD, right? And I have the open loop gain for the amplifier. So my output voltage can write it as, I can write it as what? I can write it as VD into AOL. This is my output voltage. Okay, now we will see the complete expression. What is the gain? What is the closed loop gain of this op-amp? So this is the, this is a closed loop gain, So this is a closed loop gain of the op-amp. So how to find the closed loop gain? Now how to find the closed loop gain? That means output divided by input. What is this number? That is the closed loop gain. Okay. So this configuration, you can see here my input is connected to the positive terminal, so, or the non-inverting terminal. So this amplifier is known as non-inverting amplifier. Okay, non-inverting amplifier, because my input is connected to the non-inverting terminal. Non-inverting terminal means what? If you are giving a positive supply, positive input, you will be getting a positive output. If you are giving a negative input, you will be getting a negative output. So this is what the non-inverting means it will not change the sign. Okay, non means not change the sign, but inverting means you will be getting X. That means if you are giving a positive input, you will be getting a negative output. Okay, so we will be doing the circuit analysis now. Listen carefully. So we are talking about the non-inverting amplifier. I can write like this, NI amp. Okay, non-inverting amplifier. So I will be drawing the circuit diagram here. Minus, plus, this is my V out. Same thing, RF and RI. Okay, RI. Now I can connect here to this, and this I will call it as VF, my feedback. Why? This is the feedback voltage, okay, feedback voltage. And you see here, this is my input, okay, my input V in. Now for the amplifier, we have the gain, open loop gain. We want to find the closed loop gain. But I told you my V out will be equal to, I have a voltage difference here, VD, between these two terminals. So VD multiplied with the open loop gain. That is my V out. But what is my VD? I will calculate the VD. Sorry, I have made a mistake here. This is plus, this is plus, and this is minus, okay. Please see the diagram before. It's plus and minus, sorry. Now VD is equal to, what is VD? VD is equal to, you have for the plus input, you have an input which is V in, so V in, and for the negative input you have the input VF, so minus VF. This is my, okay. And so V out, I can write V out like this. It's equal to V in minus VF into AOL. Am I correct? Now we are going to find what is V out. I told you for the op-amp, the current which is going inside I, let's say this is I1 which is equal to 0, and this current which is also I2 which is equal to 0. So all these currents are 0, so nothing to worry. It's very easy to solve because the input resistance of the op-amp is very high. So the currents are almost 0, and I told you this before. Now what is VF? VF can be easily found out by using the voltage division. So VF is the question, okay. So VF can be easily found out by using voltage division. So it is coming from V out. So V out divided by RF plus RI, and you have to multiply with this guy RI, right? That is VF. How to obtain this? You can assume the Kirchhoff law also. There is another method. You can assume Kirchhoff law here. This is I1, let's say this is I2, and this is I3. So I1 plus I2 plus I3 is equal to 0. But I1, I told you, which is going into the op-amp, it is the same current here. This is equal to 0 ampere. So 0 plus, what is I2? I2 means this is the voltage VF. So this voltage is also VF. So VF minus V out divided by RF plus I3 is VF minus, this is 0 volt, so VF by RI. This total is equal to 0. If you solve this, you can find VF as V out divided by RF plus RI into RI. Both are same, okay. You can find like this also. So I am going to write what is my V out by using this. So my V out is equal to V out, okay. I can write this VF in another way also, okay. So my VF is equal to RI by RF plus RI, same thing, into V out, and I am calling this quantity as B or beta, we can say. So this is B into V out for simplicity, okay. I hope this is clear to you. This is my, okay. Now I am going to write down the equation. My V out is equal to V in minus VF into AOL, V in minus VF into AOL, and my VF, we have got it, it's beta or B into V out, okay. So V out is equal to V in minus B into V out into AOL. I can multiply this, V in into AOL, okay. V in into AOL minus B into AOL into V out, okay. And this is V out. Now you see here, I have V out here and here, so I can take to the one side. So V out, then I will bring this guy here, so it will become B into AOL into V out, which is equal to V in into AOL. So V out is equal to V out, I can take this outside, 1 plus B into AOL is equal to V in into AOL. Now I told you the closed loop gain means what? Closed loop gain means this one. The closed loop gain is V out by V in. So I want to find the closed loop gain. Okay, I want to find the closed loop gain. So closed loop gain is V out by V in, which is equal to, from this equation I can write, this is AOL, I can write like this. I can move this guy here and I can move this down. Okay, then V out by V in will be equal to AOL by 1 plus B into AOL. So this is my gain now. You see here I am controlling the gain. Now I will write down this equation once again in the next page. So the closed loop gain is equal to the output voltage by input voltage. Okay, this is observed by one observer, I have told you, and this is observed by another observer. He is measuring here. So this output voltage by input voltage is AOL by 1 plus AOL, okay, into B. Okay, so you see here AOL is very large number, but we know that AOL is very large because it is of the order of 10 power 6. So my closed loop gain I can write, because of this reason my AOL is very large. Because of that I can write my 1 plus AOL into B is approximately equal to AOL into B, right? Because AOL is very large number. So the closed loop gain is equal to AOL divided by this 1 plus AOL. I am going to replace with AOL into B. So this has become 1, this will cancel out, so this become 1 by B, right? And you know what is B? We have B is equal to, we have already assumed what is B here. B is equal to Ri by Rf plus Ri, right? Ri by Rf plus Ri. So 1 by B is equal to, what is 1 by B? It is equal to Rf plus Ri by Ri, right? So I can write this as Rf plus Ri by Ri, which is equal to 1 plus Rf by Ri, right? I can cancel out this thing, the terms. Okay, so this is my closed loop gain. You see here my closed loop gain is equal to 1 plus Rf by Ri. It is independent of the open loop gain. Now it is independent of open loop gain of op amp. So now our op amp is free. Okay, without op amp this is not possible anyway. So what I am going to say is that you have something plus minus. Okay, I will write it. Okay, you have the circuit plus minus and you are giving the input here V in, and this is your feedback. You see there are two resistances. This is Rf and another one is Ri, and this is your Vf. So in this situation, what is the gain of the op amp? The gain of the op amp, you will be getting V out. So the closed loop gain of the op amp is, this is the closed loop. Okay, the closed loop gain of the op amp is Rf by Ri plus 1, right? Okay, 1 plus Rf by Ri. Okay, so let us assume that you put here, suppose you want a gain of 100. Example, you want a gain of 100. Suppose you want a closed loop gain of 100. So what I will do, let us assume RF is equal to 99 kilo ohm and RI is equal to 1 kilo ohm, then closed loop gain is equal to 1 plus RF is 99 kilo and this is 1 kilo. So 1 plus 99, you will be getting it as 100. Now for another example, suppose you want a closed loop gain of 1000. Okay, now I will assume that I will take a resistance of you can use anything. Okay, I will take a resistance of say 999 kilo, and I will take another resistance Ri, which is of 1 kilo. Then my closed loop gain will be equal to 1 plus 999 kilo divided by 1 kilo, which is equal to 1000, right? So you can control the gain of the amplifier. So you can fix the gain of the amplifier by fixing these guys. That's a beauty. So if you change RF and RI, if I am using RF and RI, and you see here that with this possibility we can control the gain of the amplifier. So what I am going to say is that this is the non-inverting amplifier. Okay, here actually we are controlling the gain. The closed loop gain is 1 plus RF by RI, and you have plus minus, and this is RF and this is RI, and this is V in and this is V out. Okay, so I can draw this circuit in another way also. Okay, the same circuit I am drawing in another way. Please listen carefully. Instead of plus minus, I will be writing minus plus. I will use a different color. Both are same circuit anyway. Minus plus, and for the plus I am giving the input, no change, and from the output this is V out, and from the output I have a connection. You see this connection is going through RF, this guy. So this is RF, and from RF I am connecting, this is my VF, so I am connecting to the negative terminal, and from this point I am connecting to the ground, RI. So both the circuits are same, and this is the voltage feedback. Okay, so both are same. Okay, so we will be mainly using this one throughout the course. Okay, so this is a good method. Okay, so you can draw the circuit in any way. Now the gain of this, the closed loop gain is equal to 1 plus RF by RI. So I hope that everybody understood what is the non-inverting amplifier. Now I want to tell you one more thing in this case. So let us assume that let us consider the same circuit. So I will draw this one. Okay, this is my V in. So from now on I will be drawing this kind of circuit. Okay, and this is, so what is this? This is a non-inverting amplifier. So this is my RF feedback. You see here it is connected to the output. So from the output to the input it is connected, and this is my RI, and this path is grounded. Okay, I hope this is clear to you. So this is my, and what is my closed loop gain is 1 plus RF by RI. Now let us assume that you know that the open loop gain is very high. For example 10 power 6. Suppose listen very carefully about this point. Suppose V in is equal to 6 volt. Let us assume that V in is equal to 6 volt. Now, or 10 volt, let's say. You are giving the power supply as plus VCC, which is equal to plus 15, and this guy as minus 15. Okay, VEE or minus VEE, you can say it's minus 15 volt. So you can go up to minus 15 volt. Okay, now let us assume that suppose my V out was let's say some 5 volt, let's say, okay, 5 volt. So this is my V out now. So for example, I am considering my V out as 5 volt. So my VD, what will be my VD? I told you that my V out can be written as AOL into VD, okay. That means the open loop gain into this difference voltage, okay. Now what will be this VD? My VD will be very small, right? So my VD I can calculate from the output voltage. My output voltage is very clear. So I can write my output voltage as 5 volt. So this is equal to my AOL I have given you 10 power 6 into VD is equal to 5 volt, okay. So what is my VD? VD is equal to 5 divided by 10 power 6, which is equal to 5 into 10 power minus 6 volts. Oh, this is very small number. So you see here that you can see here that my VD is very small number, which is nothing but 5 microvolt. And what is my VD? You know that this potential is V in and there is some potential here. Let's say this is VA. My VD can be written as, okay, my VD can be written as V in minus VA, and this number I am saying it is 5 microvolt. That means my V in minus VA is approximately 0. That means 5 microvolt is very small number and approximately 0. You see here my output voltage is a large voltage which is 5 volt, but my VD is 5 microvolts, very small. That means that my VA will almost be same as V in. It is like a short circuit. You know that the voltage at 2 points will be same only if they are in short circuit. But here it is not actually short circuit. They are not actually short circuit, but it seems like they are short circuit, or we can say that they are virtually short circuit. Because of this, this is approximate 0. It means that not 0. Yeah, it is approximately 0. This is approximately 0. It means that my V in is approximately equal to VA. That means they are short circuit, but it is not actual short circuit. It is because of the overall property of the amplifier or the circuit. So it is known as virtual short, okay. It is known as the virtual short, or this is the concept of virtual ground that we will see, because virtual ground means 2 points will be at virtual ground if they maintain the same potential even though they are not connected. So if V in changes, VA also will changes, okay. So this is the virtual short circuit. I hope this part is clear to you. So this is the virtual short circuit of the op-amp. So you see that whenever you have an op-amp like this, I am drawing this again, this V in, and this is Ri, and this is grounded here, and this is open loop gain, and this is okay, and V out, and this voltage, let's say this voltage is same as V in, so this is V in, and this voltage is the feedback voltage, okay, or you can say another name VA also, okay, I have used in the previous part, I have used VA, so, or VF, okay, it's same thing, okay, or you can use the notation VF. So this is a feedback voltage, I am using the notation VA now. So since VD is approximately 0, I can say that my VA is approximately equal to V in, and this concept is known as the virtual short circuit, virtual short, okay, or virtual ground concept that we will see in another amplifier, which is the inverting amplifier. And what is the closed loop gain of this? The closed loop gain is 1 plus Rf by Ri, right? Okay. So that is the beauty. So for this kind of circuit, it's very easy to solve. We don't need to have a complicated expression. You see here how did I solve this by using these methods. Okay, you can see I have written a lot of steps. So at every point of time for a complicated circuit, it is not possible to solve like this. So we will be using another method for solving this. After that, I will wind up this lecture. Okay. So we will be using minus plus, this is my V in, and this is Ri, and this is Rf, and this is V out. Okay, this is my V out. Okay, I will write it here, V out. Okay. Now I told you that the current which is going into the op amp, this current and this current, this I, let's say this is I1 and this is I2, this is equal to 0 and this is also equal to 0. Okay. Now I told you the voltage at this point is V in, because this is connected here, this is the same circuit, part of the circuit, this is V in, and this voltage is VA, but it is approximately equal to V in, right? So VA is approximately equal to V in, and I can now solve the circuit very easily. Okay, so I will be look at the non-inverting terminal, first step. I am going to look at the non-inverting terminal. And what is the non-inverting terminal? This is the non-inverting terminal. This terminal is the non-inverting terminal. You can see this connection. That means what is the voltage here? The voltage here at the non-inverting terminal, we have seen it is V in. So the voltage here, the voltage is equal to V in. Okay, we have seen the voltage. Now I told you VA is approximately equal to V in. That means that assign same voltage at inverting terminal also. That means for the inverting terminal the voltage is VA, but VA is approximately equal to V in here. In this case, okay, here in different circuit it will be changing anyway. So we got here the voltage is V in. Now write the KCL, Kirchhoff current law, at node A. We can say this is node A. This is the node A. That's why this is the node A. So I am going to write the Kirchhoff law. So what is that Kirchhoff law here? You see, I will assume that my one current is leaving from the junction. Let's say this is going here, this is I2, this is I1, and one current which is going above, which is I3. So it is nothing but I1 here in this circuit, here I1 plus I2 plus I3 is equal to 0. Okay, and for this you know that the closed loop gain was 1 plus Rf by Ri. We will check whether we will get the same answer. So you are going to write the Kirchhoff law now. Okay, so Kirchhoff law, I1 plus I2 plus I3 is equal to 0. And what is I1? We will see what is I1. I1 is the current which I am saying which is going away from the junction. So I1 is nothing but VA minus, this voltage is 0 volt. So VA minus 0 divided by the resistance is Ri, right? Plus, I told you I2 is the current going into the op amp, and I2 will be 0, of course. And I3, what is I3? I3, you know that this is the voltage VA and it is going here, and this voltage is V out. So we have VA minus V out divided by Rf, right? Rf. But you know that this is my I1, and sorry, this I will write like this. This is equal to, so this is my I1 and this is my I2 and this is my I3. Okay. Okay. Sorry. Now this is, so but we have but VA is equal to V in. So I can write, so I can substitute in this equation V in minus 0 means V in plus this is 0, VA is V in minus V out divided by RF is equal to 0, right? This total is equal to 0. That's what the Kirchhoff law means that. So we will be getting, you see here I will be putting all this V in term here. So V in into 1 by Ri plus 1 by Rf is equal to, I will put this to the right side, V out by Rf. But I want the expression to the closed loop gain is equal to V out by V in. So this is equal to, I will move the total thing down and I will move, I will move this guy. Okay, I will not be doing like this. Okay, sorry. This is my, I will be moving my V in here and I will be moving my RF onto the top. So this will become RF into 1 by Ri plus 1 by Rf. So if you multiply this, it will become Rf by Ri, this become Rf by Ri plus Rf by Rf, which is equal to, Rf by Rf is 1 and Rf by Ri is Rf by Ri itself. So you are getting the closed loop gain is 1 plus Rf by Ri, which is the same answer. That's what you are getting here. So this is your closed loop gain. So this is your closed loop gain. So you see here, with a simple circuit solving technique, we have got the same expression. So we will be using this kind of method throughout the lecture. I hope this is clear to you. Okay. So what is the procedure? I will summarize. You see here, minus plus, this is V in and this is Ri and this is Rf. That's it. Okay. Now you will see, first you will see, this is the first procedure, you will see what is the voltage here and it is V in. So in the first step, look at the positive terminal and the voltage is, identify the voltage, and here in this case it is V in, right? Now second, this mark this voltage as VA, and VA is approximately equal to V in, because you can see that the same voltage because of the virtual short. Now write KCL. Okay, for that you can assume that the currents are moving away from the junction. Okay, that's it, I1, I2 and I3. So I1 plus I2 plus I3. Solve this equation and get the expression for V out by V in. That will be the closed loop gain. Okay, like this. But there are some other methods also. You can assume the same thing in another way. Maybe Engineer Abdul Rahim will be teaching like that also. Let's say minus plus, this is V in. After summarizing this, I will finish this. Okay, Kirchhoff law, another way to apply KCL. Okay, now you see here, this is V in, so this voltage is V in, and this also is VA, which is equal to V in. Okay, now you can assume that there is no current here, this is 0 ampere. So whatever current which is coming from here will be going like this, right? So let's say this current is I into IRI, not I into Ri, it is the current. Let's say this is I1 and this current is I2. So since there is no current here in this side, there is no current, so I1 will be equal to I2, right? And what is I1? This is 0 volt and this is VA. Okay, so I1 is equal to 0 minus VA divided by Ri. And what is my I2? I2 is, this voltage is VA, and at the output the voltage is Vout. So I2 is equal to VA minus Vout divided by, this is RF, so RF. And these currents are equal. That means that 0 minus VA by RI will be equal to VA minus Vout by RF. Okay, this implies that I can replace my VA, but we know that VA is equal to Vin in this circuit here, okay, in this circuit. So I can write 0 minus Vin by Ri is equal to Vin minus Vout by RF. You solve this. After solving, you will be getting the closed loop gain as Vout by Vin, which is equal to 1 plus RF by Ri. Both will be same. So Engineer Abdul Rahim will be giving you this way. You can use any one of this method, okay? So you can assume you can use any method, okay? So what is comfortable for you? Thank you. Assalamu alaikum warahmatullahi.